So let's continue, and we have Professor Jacob Shapiro from Princeton, and that. I know that I did the title of his talk is, and he's not helping me with this. And, I got it. Yeah. So classification of disordered insulators in one dimension. Thank you. So Jacob, thank you for coming and thank you for accepting the invitation. The floor is yours.
Thank you so much for the opportunity to talk to you and for organizing this beautiful event. What I will talk about is joint work with my student Jui-Hui Chung. And essentially, what I want to concentrate on is the Kitaev table, which is a topological classification of insulators. And this goes along the general activity in mathematical topological insulators, which on the one hand, when you just discover the phenomena, you want to define topological indices, so just be able to connect experiment with something that is manifestly an integer. But then there's another analysis that you'd like to do, which is to somehow understand what are all possible values of that index. And hopefully that index is a complete invariant, namely that if two materials have the same index, then there is actually a path in between them in the abstract space of all materials that obey something. And well, that's what this table is. So this table, was devised by people before Kitaev, but Kitaev was the one who organized it in this way, and this way is a K-theoretic way. So K-theoretic, there's this big machine in mathematics, and for what reasons that we have, we would want to understand this table without using that machine. One reason is because that machine, while it most naturally is suggested by periodic systems, it does actually work also for non-periodic systems, but they still need to have a spectral gap. And when they are strongly Anderson localized, then this machine just does not apply at all. K-theory does not apply. Moreover, you could say that such an activity would be a warm-up to classifying many-body or interacting systems for which also K-theory is completely non-applicable. And as far as I'm aware, there are just no classification results at all in many-body physics. So it would be good to somehow understand this without K-theory. With disorder, right? With disorder.
So I'm not that familiar with K-theory. So you're stating that you have strong disorder, that K-theory doesn't work, but are you implying that weak disorder it's fine?
Yes. So there is, there's this notion of disorder where if this is the spectrum of your system, if you turn on disorder, then immediately Bloch does not apply, right? Your system is not periodic, but it could still maintain a gap. And when you have a gap and the Fermi energy is within that gap, then K-theory is valid. However, when suddenly the gap is closed because of Anderson localized states, that's when you cannot apply K-theory. All right, so that's basically what we want to understand, and maybe there is some intrinsic interest in classifying or in making topological classification of materials beyond K-theory, because after all, K-theory, while being very, very beautiful, is not a complete classification because it does necessarily forget certain aspects of the material in order to carry out this very convenient classification. So what we have achieved so far is a path-connected component, calculation of the first column of the Kitaev table, of the one-dimensional column, when you still have a spectral gap, but no periodicity. And we do this without applying K-theories. All right. So before I tell you about that particular thing, I just want to, for people who are, sorry, not that, this, for people who are not so much in the classification business, I want to explain just what is the context, so that even in the periodic setting, so that it's clear what at all I'm trying to achieve and what is difficult. All right. So I want to do a topological classification. So let me start with the setting, which is non-interacting electrons. And so my Hilbert space, let's say in tight binding setting, is this L2 of ZD with some n internal degrees of freedom if I want. And then a system or a material would be specified by taking a self-adjoint without a lot of loss bound linear operator that should obey a list of constraints. If it doesn't obey anything, then it just would be null homotopy. So the first constraint that I need is that of locality, namely that points that are far away from each other in space are weakly coupled, and they become more weakly coupled as the space distance goes apart. And that could be encoded in such an estimate. An estimate that the XY matrix element of the Hamiltonian decays exponentially in the distance between X and Y. And this is an n by n matrix here just because I allow this internal degrees of freedom. It's not terribly important. Okay. Then the second important constraint that I need beyond Hamiltonians being local, I also need them to be insulators. Right? I mean, we heard in the morning what happens if you're not an insulator. There's some other topological classification, but the basic Kitab table needs the insulating condition. So I'm saying that every system is specified by both the Hamiltonian and Fermi energy at which I prepare it, and it should be an insulator at that Fermi energy. Because I'm interested in disordered systems, let me spend a minute or two explaining what do I mean by being an insulator. So I want to probe the system by applying some electric field onto it, and then see if I manage to measure a current or not. And if I measure no current, then I would say it's an insulator. And how do I theoretically apply this perturbation? Well, I replace the Hamiltonian with one that has voltage on the J axis. That would be maybe the simplest way to do that. And then I turn the crank of this machine of perturbation theory to ask if this D0 is very small, what would be the first order conductivity of the system at the Fermi energy, having applied that perturbation. And okay, this is something that you can do. So if you apply the voltage in the J direction, you measure the current in the K direction, then this is the expression that you get after some work. So it's essentially going to be a sum over all lattice points of xi, xj, and then the Green's function, which is the inverse of the Hamiltonian, between 0 and x at that Fermi energy. All right. So if that thing happens to be 0, then I would say it's an insulator, and if it's not, then not. And one way in which it can be an insulator is if the Green's function happens to exhibit exponential decay between 0 and x. So that's a further property, not just that the Hamiltonian itself, but even its inverse is as well local. And if that is the case, then you see very well here, if it's the case, well, being uniformly in epsilon, you see that this sum will exist. And then you take the limit epsilon to 0, and because there's an epsilon square here, then you indeed get a 0. So an exponentially decaying Green's function is one signature of being an insulator. And when would that happen? Well, for local Hamiltonians, that would happen exactly when you put the Fermi energy in the gap. You can show that. That's called Combe-Thomas estimate.
Again, if you like the diagonal terms to be 0 or non-zero to be fine, so we can have full conductance for an insulator.
This is for systems that have time reversal symmetry. I think when you don't have time reversal symmetry, you get this expression. So this would not be the formula you get when you want to study Hall. All right, and then based on what I just said so far, I would say that the second constraint that I put on top of being local is this insulator constraint, namely that the Fermi energy sits not the spectrum of my Hamiltonian. So I will put it here, and only those systems I call insulators. And I know that in that case, the Green's function decays exponentially, and then I get zero conductivity, so it indeed deserves to be called an insulator. When you go on to Anderson localized systems, then you need to somewhat generalize this constraint in the following way. Well, then it turns out that when you have Anderson localization about that energy, then you cannot anymore expect the Fermi projection, the Green's function to decay exponentially, because there is actually spectrum near the Fermi energy. But if you take the disorder average, the second moment of it, you multiply by epsilon, then that whole thing will have exponential decay. That's called second moment condition of Anderson localization. And so maybe take that as the very criterion of being an insulator.
So it doesn't decay exponentially if it's Anderson localized?
Not deterministically, right? So when I'm talking about Anderson localization, I need to talk about a random ensemble of operators, and if I just pick one of them, I cannot expect it to actually even be well defined as I go into the spectrum, because, well, then the operator is not invertible.
But aren't all those states localized?
They are localized.
And that does not mean that it's
But
exponential.
no, but they are dense enough, so you really need this average. And that's why these formulas for interacting systems, where they have this condition without average, is not good enough to explain.
Actually, what you can do is replace the disorder average with energy average. Then you still may go to the real axis, but with no average at all, it's just not a healthy option.
It is the constant in front which actually diverges.
Right. And in that scenario, you also will generalize the Kubo formula to have that disorder average of the second moment of the Green's function. And indeed, when you have that exponential decay, then this will again be zero, and so it indeed deserves to be called an insulator. Of course, these are zero temperature insulators. All right, so you can use either the condition 2.A or 2.B. I will entirely focus in this talk on 2.A, but I do want to mention that eventually we would like to understand 2.B, and that regime is inaccessible with K-theory. All right. Then another possible constraint that you might want to put on your systems is those of symmetries, the Alfvén-Tirnbauer symmetries. So you either have time reversal or you have particle Hall. And so time reversal would be some anti-unitary operator on Hilbert space that squares to either plus or minus 1 and has to commute with the Hamiltonian for the Hamiltonian to be called time reversal symmetry. The particle Hall symmetry is again anti-unitary that squares to plus minus 1, but now it has to anti-commute with the Hamiltonian in order to be, for the Hamiltonian to be called particle Hall symmetric. And then you may have the peculiar situation of chiral symmetry, which is when you are symmetric with respect to the composition of the two operators, but not each one separately. And because one commutes there, one anti-commutes, then with chirality it again anti-commutes. So when you count all these possibilities together, you realize that there are 10 possibilities depending on which symmetries are present, and if those symmetries which are present square to plus or minus 1. All right, so you have 10 possible symmetric spaces, or 10 Morita equivalence classes, or Clifford algebras, and this is for the exquisitely beautiful part of a connection between condensed matter physics and modern mathematics, where you see all of these things combining together. So 1 locality, 2 insulator, 3 possibly symmetries, right? We want to now define a topology on this space of operators and just calculate the set of path-connected components with respect to that topology. That's the research program that you now have. So before I actually go to the disordered case, let me question.
Yeah, why only these three symmetries? Because if you stop at these three symmetries, you get 10. Why not more?
Absolutely. I mean, I'm always happy and curious to study even more possibilities. I'm at this moment, just would like to understand the Kitaev table, so that has the alpha and Zündbauer symmetries, but I'm absolutely not partial. So, we can talk about this too. Okay, so what is difficult here? What are you actually trying to fight against? So one thing that illustrates this in a nice way is the periodic case. So I'm going to assume for 2 minutes translation invariant. So I'm assuming that the matrix elements in space h, x, y can actually be shifted diagonally, and you get the very same thing. So h, x, y equals to h, x plus z, y plus z, for every x, y, z in zd. That's the periodic constraint. That's what means that the system looks the same wherever you move it. And when you have such systems that are periodic, then we know by basic theory that Bloch partially diagonalizes these systems. In math, it's called Fourier series, so that's why it's in F, not a B, whatever. And then you go, instead of being to have wave functions on the d-dimensional lattice, you get wave functions on the d-dimensional torus. And now the Hamiltonian itself becomes a multiplication operator. So, but because it still has these n by n degrees of freedom, then it becomes multiplication by some Hermitian, by self-adjointness, Hermitian n by n matrix. So now a system which is periodic is just as well specified by giving a function from the d-dimensional torus into Hermitian n by n matrix. Condition 1 of locality means that these functions are going to be very nice, right? It's called Riemann-Lebesgue lemma. So they're actually, if you have, I don't know, exponential decay, as I wrote before, then they're going to be analytic even. But, if you take a slower decay in real space, then maybe they will only be smooth or 5 times differentiable or just continuous. It actually doesn't really matter for this story. The insulator condition means that now the Fermi energy should not touch the eigenvalues of this n by n matrix for every point k in the Boolean zone. And so the picture looks kind of like this. And so you'd have maybe n bands below and some other bands above. And because you have this separation due to the insulator condition, then you could just as well specify, instead of this matrix valued, which is Hermitian, and then Hermitian matrix, you could just specify that n-dimensional space within your k-dependent Hilbert space. And if you do that, then you get to talk about the little n Grassmannian, which is the space of n-dimensional subspaces within C capital N, right? Or the space of rank n orthogonal projections. All right, and then thirdly, if you possibly have symmetries, then instead of being a Grassmannian, then maybe you replace it with another manifold. For example, in this chiral case, you should replace it with UN, the space of n by n unitary matrices. And okay, there's some complication here that if the Hamiltonian is in chiral, then the Hilbert space must come in 2 sectors of positive chirality, negative chirality, and because of the anti-commutation, you can write the Hamiltonian off diagonal form, and so a Hamiltonian is just as well specified by an invertible such operator that is local. And so after flattening, instead of invertible, you get something unitary, right? So that's why we're classifying unitaries that are k-dependent. All right. So by this periodic analysis, you immediately see what you want to take. So because these maps from the Boolean zone into the Grassmannian or to whichever symmetry manifold, because these maps are very nice, like they're at least continuous, then you immediately get a topology on this set of maps, right? It's the compact open topology. And with respect to that topology, you'd like to now maps that are continuous with respect to the compact open topology is just a set of homotopy classes from the Brion zone into your Grassmann. So if you, for example, take 2 dimensions and you talk about one band that is occupied within 2 band models, that's this choice, then you immediately see you get the homotopy classes from the 2 toes into the one Grassmannian in C2, which is just a 2 sphere. And so that's the degree of a map from the 2 toes to the 2 sphere, which is known to be an integer. That's the Chern number. In the SSH model, you should be in 1 dimension, so the Brion zone is a circle, and then maps from the circle to UN are classified again by a Z index, which is the Zach phase. It's just a winding number of the determinant of the matrix. I want to emphasize that in understanding things like that, I'm not only giving you a numerical formula, I'm actually telling you what is all possible classification that you can find. That's kind of the point that you see in the topology. And another point is, if you're again in 1 dimension, but you do not have chiral symmetry, then your target space is just the Grassmannian, and it's clear that because the 2 sphere is simply connected, then you get nothing, which indeed you know that in the non-symmetric 1-dimensional case, the P-type table says you should get nothing. So maybe the last thing I'll say in this is that in 2 dimensions, if you have time reversal symmetry that is equals to -1, then that symmetry operator actually defines quaternionic structure. So you should talk about a quaternionic Grassmannian, and that thing is known to have a Z2 index, which is exactly the Foucault-Millet index. So you could see it also like that. So that yes, question.
Yeah, in 1D when you have the equivalent of this, I think it's because by the time reverse polarization or something like that, like a Z2 classification.
There is that also, yes.
And then time reverse symmetry.
Not time reversal, but I think it's particle hole. It's the Majorana chain. You do have a Z2 vector index.
Okay, so the temporal classification does not give an invariant for the time reverse polarization.
Let's check. We can just check this easily. So if you want time reversal that's equals to -1, it's class A2. It's non-homotopic.
So how do we understand this?
Here you see that you better you better have this.
So the
That's that you can find it too.
I see.
I mean, if this 2-dimensional toes were replaced with a circle, then you should get a 0.
You can define in 1 dimension, you can define a pump, like a Bowers pump. So you can have, if you have Hamiltonian, which is a function of another parameter, then you can define the change in non-reversal polarization.
So only that is classification variant, but the slice of that pump is not.
One question, Jacob. So this T2 was the action of the time reversal?
T2?
Because if it's not in moment, it's just this table has this double condition, which is the table you have is using the T is acting on the circle and on the tori.
You're right.
So if you do this one, you're calculating the quaternionic gate here, the tori.
This should be equivalent maps.
Exactly. So you need to, if it's equivalent, I believe it is. If it's not, then I believe it's 0.
I don't want to insist on this too much.
No, just somehow, because if you don't put it, then the numbers flip.
That's right. I agree. So so that's just a flavor of what you're hoping to find. But now I'm hoping to find it without doing block. So that's the moment where I would stop using the slides. All right. So the first thing is I would like to concentrate on 1-dimensional systems.
I'll just change the marker. That one, I don't know why.
All be the same.
All be the same.
Really? No, they Then take the ones on the podium.
Oh, on the, okay.
That believe those ones are.
So for one-dimensional systems, I'd like to introduce another notion of locality. And why do I want to do that? Because, you should do something to make your life easy. If you don't do anything, you'll just be sweating, and it's just not very nice or interesting. And I think, most of the physics is still captured. It's just that the analysis is more beautiful. So let's do it. So usually we would put locality as this constraint, right? But now we are in 1D, so the x and y are in z. And I'd like to replace this with a consequence of this condition, so it's weaker. And how will I define it? So here is z, and let me single out the point 0, and let me project into all positive sides, right? So I call that projection lambda, projection onto the span of delta x, where x is positive, right? This is what I would call a switch function, or just heaviside function on the position operator. And it turns out that when you have that kind of locality, then one thing that is true is you can divide your operator into the grading that is afforded by dividing the system into left and right, kind of like when you're doing bipartite entanglement. And then I would write h left left, h right right, h left right, and the star. And it turns out that when you have that form of locality, then these off-diagonal elements, which correspond to how the right side speaks to the left side and vice versa, these are compact. So exponential locality implies that HLR is compact.
What does that mean?
What does it mean to be a compact operator? It means that you are, for example, one thing is that you are the operator norm limit of finite rank operators. So to practical purposes, you can imagine that you're basically restricted to a box in space, or you at least a limit of that in operator norm, and that would be fine. So the idea is that these off-diagonal elements are kind of not very important. They're not zero, actually capture something important about the system, but they're not extensive. And so let me now give another definition of locality. I would say that age is local if the commutator, lambda age, is compact. And the commutator, when you calculate it with this 2 by 2, it's exactly the off-diagonals. So it turns out that when you pick that weaker form of locality, namely saying the left and right don't talk to each other too much, that weaker form of locality affords a very nice and convenient way to carry out topological classification. Okay, so let me explain that. So classification of lambda local unitaries and projections. So before I even begin, this is just math, right? You can understand it without any reference to physics, but why would it be interesting to us? Because the unitaries for us would be the flat Hamiltonian, but the flat chiral Hamiltonian, which is now specified by the off-diagonal block, which, because it's flat, it's unitary, not just invertible. And if you don't have chiral symmetry, then the projection will be the Fermi projection. All right, so that's what we'd like to classify, but now locality for us will be compact commutators. I say that lambda is any non-trivial projection on Hilbert space. And now Hilbert space is some abstract separable infinite dimensional Hilbert space, and I say that the projection is non-trivial if its image and its kernel are both infinite dimensional. So this particular choice of lambda certainly satisfies that, because its kernel is the left, which is infinite, and its image is the right, which is also infinite. So that's good. And then I say that an operator A, which is bounded linear operator on my Hilbert space, is lambda local or just local if I have the compact commutator condition. And clearly, if one of the kernel or the image are finite, then it's automatically true. So it's just not interesting. That's why I need the non-triviality condition. All right. Then I call such operators, the space of these operators, let's call it script L of these local operators, script L sub lambda. And a very easy thing that you can verify is that this L is a sister algebra. In particular, what that means is the operator norm limit of things that sit in L is again in L. And that's very nice. For example, one thing that is a consequence of that is when you apply the continuous functional calculus to this type of local operators, you're again local, right? Because the sister algebra preserves the continuous functional calculus. So on such operators, let me define now a super operator, which is this blackboard lambda, which is derived from lambda. It's going to take an operator A into a sandwich with lambda. So what is it doing, basically? If I have the grading lambda to left and right in this concrete example, but otherwise it's just abstract, so I can always write any such operator A is ALL, ALR, ARL, and ARR. And basically this sandwich, what it is doing is it is keeping this guy as is. It's deleting the off diagonals, and it's setting this guy to the identity. Right? That would be lambda, blackboard lambda applied on A. Alright? And now one thing that you can verify is if I take this blackboard lambda and I apply it on anything that is both unitary and lambda local, then the result of that is Fredholm. Should I say what that means? Thank you, that was my question. So Fredholm means operators F where the dimension of the kernel of F is finite and F star also finite, and moreover the image of F is closed, which roughly speaking means that there's no accumulation of eigenvalues towards 0. And if you have these three conditions, then you call your operator Fredholm, and because you have two finite dimensions here, then there's an index associated with such operators. The index of a Fredholm operator is precisely the difference of the two dimensions of the kernel. So this Fredholm index has been used extensively in studying non-periodic topological insulators. Emil, who's sitting here, has been a pioneer in that. But I guess the first guy was Jean Bélissard, who really started this. So that theory very naturally leads to studying Fredholm index as a generalization of winding numbers, of Chern numbers, of whatever have you. And so it turns out that if you take unitaries that are also local and you do this surgery to them, then the result is a Fredholm operator on which you can calculate the index, right? And how do you study that? Well, one way to think about Fredholm operators is that this means that you are not injective, this means that you are not surjective, and so but the way in which you're not is finite, even though the Hilbert space is infinite dimensional. So I'm basically asking for a very benign form of being not invertible. So Fredholms are kind of almost invertible up to some compact perturbation. And so in order to show that any operator here that's both unitary and local, and I do the surgery to it, is Fredholm, I would find an almost inverse to it, which is called parametrics. And in particular, lambda blackboard U star is the parametrics of lambda U. And so if I manage to show that, how do I show that? By the way, I calculate 1 minus these two. And I show that this is compact. And if I do that, then I manage to show that it's Fredholm. This is called Atkinson's theorem. So what I'm trying to convince you of is that these operators, U, that are both unitary and local, they carry an index. And that index is precisely the index of this blackboard U. Okay, so, and that index, I'll call it the lambda index. And actually, just like the Fredholm index, which is logarithmic, also the lambda index inherits this logarithmic property. So if I have uv, this is the sum of the two indices. And that's very convenient. Next, I want to maybe possibly have symmetries. Okay, all that structure was about locality and possible indices of unitaries, but now I want possibly to add symmetries. And we abstractly we would say that C and J are two anti-unitaries, on my Hilbert space. C would square to +1, and J would square to -1. Okay, and if I take that choice, then C defines for me a real structure on the Hilbert space. If I take this choice, then J defines a quaternionic structure on my Hilbert space. And so it would be natural to now look at the real bounded linear operators. These are the operators that commute with the real structure. And same with the quaternionic structure. But it turns out that there's more interesting spaces beyond just these most natural ones. For example, maybe you want to have star real or star quaternionic. What do these mean? That means that you commute, but after you commuted, you need to add a star. So it's AC equals to CA star. And the same for the quaternionic version. AJ equals to JA star. And moreover, I want also to consider imaginary versions of these spaces, where I anti-commute with the symmetry operator. All right. So with these 6 spaces, and together with the complex one, I have another version, I see that I have all possible combinations that maybe could be interesting. I mean, Emil, maybe if you implement different symmetries, then there's more, but with the Alpha and Zirnbauer, this kind of exhausts everything that you might need to study. Okay. And moreover, I'm going to assume that that C and J commute with lambda. So they're not just local, they're actually hyperlocal. That's going to be convenient. Probably you can generalize this, but let's for now assume that they really act within the internal degrees of freedom, so they're hyperlocal. One thing that I'd like to mention briefly before I go on to the classification is, I said what is the Fredholm index, which is one way in which you can rephrase the non-periodic Zach phase or non-periodic Chern number. You can write it like this. But how do you write the Foucault-Millie index when you don't have periodicity at all? So in order to do that, you need a Z2 version of the index. And there is such a thing. It dates back to 1969, although in condensed matter physics, I think Hermann Schultz-Waldes first used it in 2015. But anyway, there's a Thier-Singer Z2 index, which they introduced in the 1969 paper that kind of classifies all symmetric Fredholm operators. And what is the idea here? The idea is that if you calculate the index of anything Fredholm, but which is more of a star version, so it's either star real or it's a star quaternionic. So I'm going to write star and then some field, and the field will be either the reals or the quaternions. Then that thing is automatically zero, turns out. Why that? Well, you see that you have the dimension of the kernel of F minus the dimension of the kernel of F star. So in particular, if you calculate something self-adjoint, then you immediately get a zero, right? And because of this star, you can relate the kernel of A to the kernel of A star. They are actually isomorphic, so you'll always get a zero in this case. Moreover, you can convince yourself that if I calculate the index on anything that is self-adjoint, that also is maybe real or quaternionic, I also get a zero. But Thier and Singer realized, and also in solid state physics, it was realized in 2005 that there's still something interesting in this scenario. And so what they did, they said, okay, let us then define the index sub 2 of an operator that would be the dimension of the kernel. But that thing is not continuous, it's only lower semi-continuous, that you have no hope. However, it turns out that if you calculate mod 2 of this thing, then in some symmetries, this is a well-defined index in the sense that it's norm continuous and compactly stable. And so that is the object to have, to study. And so a claim that I make, and was proven here, is that on Fredholms that are star quaternionic and Fredholms that are self-adjoint and imaginary real, the index 2 is well defined. So that's another notion that in which one would like to phrase the Z2 indices. I want to also alert you that unfortunately it seems like there is no logarithmic law for that Z2 index. All right. So with that, I'm ready to phrase the classification here.
So in that claim, you would like to be a little bit stronger, saying that this C2 index identifies all the connected components.
Right, it's a complete invariant. Indeed, that's what they show. And that's what they will also show right now.
By logarithmic law, you mean the product of two Fredholm operators is not the...
Correct.
Okay.
This thing.
Yeah.
All right. So now here is pi 0 of unitaries that are local, but these unitaries that are local would have some symmetry constraints, so they are in one of these fields. All right. So the statement is there exist 5 bijections that basically calculate for you the path-connected components of this space of local unitaries. So the first 2 are that unitaries that are complex or real and local are indexed by z, and that z is precisely that index. So I could write that this lambda index lifts to a bijection, and that's for f real or complex. The third bijection is that this same index on quaternionic operators is always even. You could say the even integers are bijective with the integers. Why do I bother to say that? Well, because that same formula is just always even valid. That's all I'm trying to say. The fourth bijection is that a star real unitaries are null homotopic. And the most interesting one, for me at least, is that the star quaternionic unitaries, which are local, are bijective with Z2. So you actually know that the Z2 index is a complete index. All right. And you also get, at least for the non-trivial classes, you get a numerical formula. So I want to make some comments about this statement. First, that it's not totally new. So number 1 dates back to Carey-Hurst and O'Brien in '82. There's a paper in Journal of Functional Analysis where they proved that any classification of unitaries that sit in some ideal, so compact operators are an ideal in the sense that if you take something and you multiply it with compact, you get again compact. That's the ideal property. So they study abstract ideals in the Hilbert space, and they managed to show that such ideals that are unitary are classified by Z index. So that was already known, but the proof there is much more long. It's longer because it's more general, right? We only need the compact ideal. That's the first thing. The first thing. Then I want to put this in context, in the sense that, well, if you drop locality, then this is very classical, right? So, for example, there's a statement by Kuiper that dates back to '65 that says that the path-connected components of unitaries are nothing. So, in infinite-dimensional Hilbert space, all unitaries are connected. That's what Kuiper is telling you, and it says that locality is crucial. If you drop locality, then you see nothing, right? Which makes sense. Right? It's like if you don't ask for continuity, then you don't have a winding number, obviously. Next, there's a study by Attia and Yannick that says that Fredholm operators are indexed by Z. Actually, the theorem is more general, but you can conclude this out of it. So somehow Fredholms are like the less regular version of the unitary locals that were, in some ways, I can explain this later, but in some ways, Fredholms can be considered as edge systems.
So you hear about strong topology only, right?
Right, sorry, thank you for the comment. 5 bijections with respect to operator norm topology. That's important. That's one result of this theorem. That actually it is the subspace topology from operator norm topology that gives you the Kitaev table on the node. That was not clear beforehand. So Atiyah and Yenich, in a sense, already understood all Fredholms, actually all symmetry classes of Fredholms. That was in 65, and then Atiyah Zinger, the symmetry version in 69. All right. And then what is it that that this would be an example of? So I mean, everything I said so far is kind of abstract and maybe hard to grasp. So let me bring it back to Earth with the example I started with. Should not delete that.
Atiyah automatically connects us to K-theory, right?
That's correct. That's correct. That's good comment.
It's just a spectrum of K-theory.
Right. So it's saying that if I have a manifold M and I take it to Fredholm operators on Hilbert space, then that's K0 of M. Right. That's the full glory of Atiyah. Right. So the example that I started with actually is that the Hilbert space is L2 of Z, and the projection, the non-trivial projection, is the Heaviside step function on the position operator, so it just projects to the right-hand side. And if your unitary is periodic, right, that's a very special case, then it turns out that the lambda index that you could calculate on it, if it's periodic and local, then the lambda index of it is exactly the winding number of the symbol associated with U, right? Basically, the Bloch transform of U, right? So that statement that connects the non-periodic setting, that thing, at least on Wikipedia, it gave me a whole bunch of names: Klein, Gochberg. If you have better knowledge, Emil, Vidom, Davinat.
No, we always start through names.
All right. So, okay. So that's just a concrete example that actually, what you're doing is actually calculating the Zach phase, and sometimes it would have like interesting symmetries for this Zach phase, where I wouldn't know how to phrase it in terms of a winding number, right? Then I know only how to do the index 2, but this is index 2 lambda. But basically, this is like the non-periodic version of the Zach phase. Okay. So what I would like to do in the time that I have left is explain just number 1, because I find it really cool. But maybe before I do that, I have like 8 minutes. So
I have a question. Why you put this strong topology, the operator norm, which is uniform convergence? Because there are problems with that. When you want to do mappings of mappings, this is not well behaved.
It's not the strong operator topology.
No, the good one is the strong one in some sense. The good one for many properties.
Maybe.
This is very small. Poles are very small.
This turns out to give you the Kitaev table.
No, the other one also. Just this one has. If you do mapping, say you take the Hilbert space of sections in a circle, and you want the rotation actions, not continuous.
Yeah, I agree. And then there's also other, like for example, if I have a sequence of functions and then I apply it on an operator, then the convergence is in strong operator topology, but not in norm topology. I agree that in 1D it turns out to work. And by the way, it's absolutely not true that if you're asking about the classification of Anderson localized, then this is going to break down, right? That's not the correct thing to do. It is very clear. But at least here in the spectral gap regime, turns out to work.
Yes, yes, yes.
Before I say something about the proof of one, as much as I have time, I want to just phrase what happens in the other symmetry classes, right? Because these are only 5 bijections, but we have the one-dimensional column is you need another 5 bijections. So what do you do there? So for that, I want to talk about self-adjoint unitaries, or ZAU, for short. If you speak German, then it should be funny too. What are these self-adjoint unitaries? Well, the flat Hamiltonian, right, is if I apply the sign on the Hamiltonian, then it's both self-adjoint and unitary, has eigenvalues plus minus 1. And now I should classify these guys, which is equivalent to classify Fermi projections at 0 Fermi energy. It's equivalent to classify Fermi projections, and that's the thing I should classify if I do not have chiral symmetry, right? So I need to produce for now 5 additional bijections with self-adjoint projections. So first I would say that ZAU is non-trivial, just like projections were non-trivial when the 2 eigenspaces, 0 and 1, were infinite dimensional. ZAU is non-trivial if the plus minus 1 eigenspaces are infinite dimensional, right? And it's clear that you should be talking about non-trivial self-adjoint unitaries, because otherwise something weird is happening with your Hamiltonian. And now I would need an additional constraint on my Hamiltonians. It turns out this is like a new input to the theory that I'm giving you now. That I'm proud that we discovered this. So what is the input? It turns out that if I now try to classify ZAUs that are lambda local, that have a compact commuted over, the result is not what the Kitab table says. Right? For example, you expect that if there are no symmetries at all, right, then all ZAUs should be connected. But that's not true, it turns out. And why is it not true? Well, it's not true because of finite dimensional defects, right? If somehow something bad is happening, but it's only finite and only on the left, then you wouldn't be able to connect it with. So that motivates the following definition. I say that a ZAU U in S is the space of ZAUs, is lambda non-trivial, right? That's a new notion for me now. If basically it's a non-trivial ZAU on the left and on the right separately, right? That's what it's. I'm asking that it be infinite dimensional, basically on the left and on the right separately. That's the class of systems that I want to classify. So if there exists some V in S such that V is completely diagonal in left-right decomposition, and the difference between U and V is compact, and VLL, VRR is a non-trivial ZAU. So it turns out that you really need this non-triviality to actually get the Kitab table. And what does it mean? It basically means that you should be honestly a bulk system, right? If somehow the plus or minus eigenspaces on the left or on the right are finite dimensional, then you're really not a bulk system. You really should get an edge classification, which is different. So that's what this is asking for. It's asking that you're really a bulk system. Now you ask, why wasn't this necessary for unitaries? Well, because it's automatically true. There's a theorem that we state that basically says that unitaries that are lambda local are automatically lambda non-trivial. And that's why I didn't need to talk about this complication. And so now for ZAUs, I have the following additional 5 bijections. with respect to operator norm topology. And those are 6, 7, 8. ZAOs, which are lambda non-trivial, and furthermore are either real, complex, or quaternionic, are nothing. They're not interesting. So that's, in particular, the complex case is the no symmetry case of the Kitaev table. And then there is a very interesting index that's the Kitaev number of the Majorana chain. When basically you are imaginary real. And then lastly, the imaginary quaternionic is again nothing. All right. So you, together with the other 5, you now get the full classification of the one-dimensional column of the Kitaev table. Again, before I finish, I realize I'm out of time. I just want again to give credit. So number 6 for the complex case is not new. However, it's relatively new. Andruchov and collaborators in 2015 in Journal of Functional Analysis, they actually have classification of all ZAOs that are lambda local, not just the non-trivial ones. And actually then they find also some interesting things. That's exactly these finite dimensional defects. So they already understood that. But we did the symmetry case. The same here. And I would like to say that the symmetry case, when you are just real or quaternionic, is not a very dramatic generalization, even though here our proof is different than that of the Hurston-O'Brien. But it is the Z2 proof that is really quite distinct. So I'm apparently out of time, so I cannot tell you about the proof of 1, but privately I would be happy. Thank you for attending.